have been published in journals in statistics, economics, business, computer science, information theory, neuroscience, and biology. Okay, and yes, and today's title is High Dimensional Knockoff Inference for Time Series Data. Please start.
Thank you, Yoshi. First, I want to thank everyone for being here. And well, the original plan was for me to visit Yoshi because I'm on sabbatical this semester. And but given current situation, so now it's a virtual visit. So I really appreciate Yoshi for kindly hosting my virtual sabbatical visit, and also for the extremely kind introduction. And today is my great pleasure to present my recent work at this forum. And this is a joint work with Yin Fan at USC and Jinchi from Taiwan. He was visiting Yin and me for a while, and I think he's joining Academia Sinica as a junior faculty. And also is joined with Qin Kang Yin from National Tsinghua University from Taiwan. Also feel free, to stop me at any point. It's always good to have a conversation instead of just doing like a pure presentation. Here's basically a roadmap of what I plan to talk about today. I'll start with a motivating example, explaining a little story behind why we were interested in this project. And then I'll present the main idea of the method, so-called time series knockoff inference. Followed by some theoretical understandings. If the time allows, I'll go through some numerical studies to showcase how this method might perform in the some simulation and real data example settings. As we know, there's lots of recent data science and AI applications, for example, in medicine and economics. And this kind of applications or data sets commonly involve large scale features, which means oftentimes we can collect information on individuals like ourselves, right? For example, for health profiles. But you can imagine it's very easy to collect lots of features, for example, phenotype and genotype, right? And if you look at single cell scale, there's a tons of data, not to mention, for example, brain imaging data, right? It's trying to understand the functionality of the brain as a network because there's billions and billions of neurons. So it's a lot of features we can potentially leverage to understand what's driving basic prediction for a variable we're interested in. For example, in economics, you might want to forecast basically inflation, right? So we know that globally, the situation is getting more and more concerning if you look at CPIs from different countries, right? Okay, so of course, there's many methods we can use for this kind of modeling and also for feature selection. At the same time, when you're trying to do prediction, you want your model to be first, well, it basically has interpretability, which means that you don't want to use all the features for prediction because the interpretability might be a big concern. It's very difficult. At the same time, on top of interpretability, we also want to have stability. Well, think about an AI system, right? Suppose you want to design a auto-driving system, and presumably we're throwing a lot of training pixels, right? For example, you have images in different conditions and different weather conditions, geographic locations, and different actions, right? For example, streets, pedestrians, cyclists, right? So all these different scenarios. So hopefully after you throw in all data into an AI system, the system can learn the underlying features to do accurate prediction, which means that you want to find the hidden and latent useful features. But if you think about the prediction alone, even if we miss some like a causal, quote unquote, of course, it's very difficult to argue what is causal, right? But the two underlying useful features, even though miss that, you find a good proxy, say under this kind of environments. So another feature, which is spurious, can be a good proxy to the underlying true feature. the predictive system, AI system can still do a good job, right? But imagine if you deploy basically the car powered by AI auto driving system to a completely different environment. Imagine it could be on Mars, right? Or different planet or a completely different weather situation. In that case, you might imagine that a system might not be stable because if we miss some of the truly useful variables. So I hope that it could give us a good little bit of intuition behind why we care about stability for prediction problem, because we want to enforce and stability, meaning that we want to control the error rate, right? And of course, there's many ways to measure how good a selector is in terms of, for example, a different way to define the error performance. In particular, FDR, false discovery rate, has been so popularly used over the past 2 decades, not only in statistics, but also in economics and also medical sciences in all the different fields. And so this work was originated by the influential work by Benjamin and Helgeberg in 1995. There's lots of follow-up works. And if you apply this FDR framework, at least the classical one, so what we need is basically justified p-values, which means for every feature, for every hypothesis, we want to test the amount of evidence contained data against the null hypothesis. Smaller p-value meaning that maybe it's more likely that the data might be inconsistent with the assumption we have in mind, right? So, but if you think about complicated learning tools, for example, these days, non-parametric learning has become so popular in, for example, machine learning, data science, AI applications, right? So if you want to apply high-dimensional non-parametric learning methods, the first question is, how do we get the justified p-values in order for us to apply, for example, FDR tool? If you do a search, you might realize that the current literature on this topic is very scarce, which means even for popular methods like random forest and also deep neural network, DNN, it's largely unclear how to come up with justified p-value. Of course, heuristically, there could be different ways to construct feature importance measures, right? Even for random forest, there's different ways. But how do you come up with theoretically justified p-value is a big question mark, at least for now. And as alternative, there's a new framework that was proposed by Rena Barber and Emmanuel Canas about 7 years back in 2015, so-called knockoff filter. So actually it's a novel way for FDR control, and it's based on completely new idea. So the knockoff filter was originally proposed in a setting of a low-dimensional Gaussian linear model. For example, if you assume a linear regression model, and if you assume, for example, Gaussian error, of course, that is a good starting point, right? Lower dimensional means that the feature dimensionality is upper bounded by the sample size. And the knockoff filter original construction was based on the geometrical structures, which means, again, I'll review a little bit details about this kind of methods in a second, but at a high level, so knockoff variable means basically the fake variable. And but the fake variables basically mimic the structure or original features. For the geometrical construction means, the maintained geometrical angle. All right. So again, when I introduce some example in a second, and this will give you more details behind this kind of methods. Okay. So and okay. Recently, there's basically extension of original knockoff filter work. Basically, it's a so-called Model X knockoffs. So, so the idea is instead of geometrical construction of knockoffs variables, and so this work basically introduced a new way to generate knockoffs variables probabilistically. Again, I'll give you some intuition with some simple examples in a second. And if we move from geometrical to probabilistic constructions, One other thing is we can have basically FDR control for general high-dimensional nonlinear models, which means first one go beyond linear models, from linear to nonlinear. Second one is actually not only we can deal with case when the dimensionality is bounded by sample size, but also can go beyond that. And also for the knockoff inference framework, one key innovation is basically completely bypasses the conventional p-values. As I mentioned, like a few minutes back, right? So even for like very popular tools like random forest or deep learning, it's unclear how to provide justified p-value. So actually, if for example, you step back and work with more popular and simplified nonlinear models, and you can do some exercise and also search the literature. So getting justified p-values oftentimes is not an easy task. With knockoff inference framework, it can deal with arbitrary dependency between the response and the features. That's why basically it's general nonlinear structure. But of course, everything comes at a price. The price we pay for such generality is we don't have basic knowledge on the underlying covariance distribution. So for example, in original work on Model X knockoff, there's one major assumption saying that we have full knowledge of covariance distribution, which is p-dimensional distribution. And based on that, we can do lots of construction, and then we can do inference. Of course, you can ask what happens if we don't know such information. There's also related literature, which I'll briefly talk about in a second. To gain some intuition about this knockoffs idea, so here basically I want to start with a simple example for a Gaussian data. Before, oftentimes when we work on a learning problem, starting with the Gaussian distribution can give us some simple, oftentimes give you some deep insights. All right. So in this case, basically we assume that we have a p-dimensional feature vector x, x1 through xp. And is normal with mean 0 and also a covariance matrix sigma. If you work with Gaussian data, the construction of Model X knockoffs actually is very intuitive. If you like, and think of this as a twin of the original feature, for example, which means for every xj, we're trying to create a copy, a fake copy of xj, which we call x tilde j. So it's actually, it's better to understand this as non-identical twins in the following sense, meaning that when you look at a pair xj, which is original, and x tilde j, in my talk, whenever you see tilde, that means fake variable, knockoff variable, it's a copy, it's a non-identical twins. All right. So the idea is, of course, there's so many ways to construct the fake variable or something called Model X knockoff variables, but we want to have a nice property like with respect to all the remaining features and also knockoff features. For example, if you look at the variable j, right? Of course, we have p-1 variables, and also we have the p-1 knockoff counterparts to the eyes of all these guys. So xj original and x tilde j, the knockoff variant, they're indistinguishable, which means the symmetrical, and which means if you swap the two, you can never tell which one is original, which one is the knockoff variant. And more formally or mathematically, such basically the property so-called the joint distribution of x and x tilde. Again, x contains the p original features. X tilde contains the p knockoff features. This admits exchangeability on the swapping operator, which means whenever you pick a subset of the p features and you swap the original feature with knockoff variants, and the joint distribution stays the same. So that's why what I mean basically non-identical twins, which means to the rest of the guys, these two are basically the same, right? But of course, I put basically a modifier here is basically non-identical. In a second, we'll see why we cannot create for simply create identical twins. In that case, we can run into issue, right? And in fact, under the Gaussian distribution assumption, the construction of Model X knockoffs can become really simplified. the main idea is we're trying to construct X tilde such that the joint distribution stay the same whenever we swap original variables with the knockoff counterparts. So mathematically, the sampling actually is pretty straightforward in Gaussian case, which means we condition on the original feature X, and we generate X tilde, which is the knockoff feature, which is basically the fake variables. It follows Gaussian distribution with mean X with original feature minus diagonal of S, which means we pick, say, P non-positive values, at least non-negative values, and the diagonal matrix times the middle guy is the inverse covariance, so-called precision matrix, and multiplied by the original feature. And covariance matrix is 2 times diagonal matrix minus this guy. Again, involves basically two quantities. One is the precision matrix, which is inverse covariance, and the other one is diagonal matrix. So for this diagonal matrix, all the entries should be non-negative. So actually, ideally should be positive. And ideally, we should make this guy to stay away from 0 as much as possible. So that's why I mentioned the non-identical twins, because if this guy is 0, everything 0 on the diagonal, so X tilde will be equal to X, which means even to parents, there's no way to tell who is who, right? If we have 2 identical twins. Statistically, this diagonal matrix S actually controls the power, which means if you were trying to make the original feature Xj and the knockoff feature X tilde J deviate from each other, then we have more power for testing. All right. So putting things together under the Gaussian situation, so X tilde, which is knockoff feature, X is original features. So if you put it together, actually we have a very simple joint distribution. It's normal with mean 0, and so sigma is original covariance structure. And the reason why I said basically is non-identical twins of the original feature, because to every all other features, you see, basically it has same covariance structure as original feature. So this block actually is also sigma. And not only this block sigma, if you look at the this block, the cross covariance, so it's still sigma, copied basically same covariance structure. But if you look at diagonal, which means if you look at pair J and it's not going to copy, we want to make sure there's some distance between the two. That's why we subtract a non-negative number, hopefully a positive number S. All right, so that's basically the joint distribution under Gaussian assumption. As you can see, along as we're willing to work with Gaussian data, the sampling of mod X knockoffs actually is, in this case, actually is not too complicated. Of course, in practice, we don't know the covariance, right? We don't know true covariance sigma. We don't know the true precision matrix, but we know that there's a huge literature dealing with estimation covariance and precision matrix, which means you can easily plug in your favorite covariance estimation method, trying to do sampling under this Gaussian setup. Related to basically the question of, as I mentioned, basically original Model X knockoff paper assumes that the covariance distribution is known, but in practice, it's almost never the case, right? So unless we have a big data to learn the joint distribution. In practice, we don't know this one. We need to estimate distribution from data. So the question is, what happens when we don't know the, for example, even for Gaussian situation, right? If we work with Gaussian graphical model, we don't know the true precision matrix omega, and we need to estimate from data. What happens, basically FDR control property of this method, and what about power? And these two questions were addressed in this work, in recent work, in a Gaussian graphical model setting. And if you go beyond Gaussian distribution, for example, for an economic data, factor model structure is so prevalent, right? So which means if you look at lots of asset returns, equity returns, they could be highly correlated, but underlying space, there could be a small number of factors that can drive the dependency of this kind of variables. So in recent work, Yoshi and our co-authors, we looked at the question of how to generate Mod X knockout variables without knowing the true distribution, we use the fact structure, and the sampling actually is very easy to implement, and we're able to justify the FDR control in asymptotic sense. And also we had a power study. Okay, so to quickly summarize what I just talked about, Model X knockoffs generation using Gaussian data. So usually we have basically a design matrix X is n by p because we have n observations on n individuals and our p features. And it's very common to start with assumption of independent rules, where typically is like all the rules are RID following a distribution. In such a scenario, the construction knockoff data matrix X tilde, because we have X tilde 1, which is knockoff copy for first feature X1, and also X tilde P, which is the knockoff copy for the last feature XP. In this case, as long as we have IID assumption, the construction of Model X knockoffs are reduced to a row-wise one, which means every time it's pretty straightforward. We condition on one row Xi. And if you look at design matrix, we fix we condition observations on individual I. We can run the Model X knockoff algorithm to generate the corresponding knockoff variant of this feature vector. And if we do that, because we have Gaussian distribution assumption, because on earlier slide, I mentioned joint distribution of X tilde, right? And you can verify that if you do that, indeed, the knockoff variant X tilde and original variant Xj, they're indeed symmetrical with respect to all remaining features. Because symmetrical meaning that they all maintain the same angles to the remaining variables. Because for Gaussian distribution, we know that the population correlation structure can be understood as geometrical angles. Okay. And another fact I want to mention here is, recall that during the entire process of the Model X knockoff generation process, right? So we never look at information in a response vector Y. So meaning that we maintained this property. Conditioned on the observed feature vector, our knockoff feature vector X tilde is independent of the response variable, because virtually we cannot go back and change history, right? And by this, we know that by nature, the knockoff variables are also null variables because they're fixed variables. They have nothing to do with our response, right? And if you put these two properties together, that is basically key ingredient for Model X knockoffs. And actually, it's easy to go beyond Gaussian distribution. And again, I started with Gaussian distribution because it's easier for us to develop intuition. So natural question is, what about the situation of dependent rules? For example, if you work with time series data, right? So we no longer have like independent rows or IID rows. So we want to go beyond IID settings. So again, let's start with a simple motivating example. All right, in this case, we work with Gaussian design matrix. And this is more like in parallel to what I just briefly mentioned. Okay, so we have n by p design matrix X. And so now we have the covariance matrix for this random matrix. So it's a tensor product of sigma R and sigma C. The first component represents the row dependency structure, and the second guy represents the column dependency structure. In the early example, this guy is called identity, but now we assume that sigma R is not identity, so which means that there's time series or serial correlation across the rows. Okay. The question is, how do we go about the construction of Model X knockoff variables in this situation? Okay, so let's do some simple thought process. Okay, so given a time index t running between 1 to n, so now we have a row xt, right? For example, this is basically returns we observe at today, right? By the end of today, we have x, say xt. We can still call the algorithm, the Model X knockoffs, basically the generation algorithm. We can construct x tilde t. Every time we grab the row xt from this design matrix, and we condition on this guy, we call this algorithm, and we generate X2.T. Of course, after you do that, you can put things together, right? Which means that row by row, we can start model X and X variables. And X is n by P because the original design matrix. X tilde is n by P because for every feature column, we need to create a fit column. Again, you can think of the fit column as a non-identical twin of original feature because it maintains the distributional exchangeability. Okay. What I just mentioned actually is a very simple way for construction, right? Very simple algorithm. And you might hope that this idea could work, which means that in the end, we have a valid or close to valid model X knockoffs data matrix. But again, let's do some logical reasoning here. So suppose this claim is true, which means that what we basically witnessed actually the simple algorithm, it just works. Then by the probability model X knockoffs, the joint distribution of X and X tilde, again, X is n by P design matrix, X tilde is n by P knockoff data matrix. So every column is a copy of the original one. Copy is quote unquote. It's basically is non-identical twins. So it should have basically distributional exchangeability, which means that whenever you swap original variables, original columns, and their knockoff counterparts, the joint distribution stays the same. Because that is the fundamental property to show that the FDR, again, I will explain the full definition of FDR in a second. FDR can be controlled exactly as finite sample levels, right? So, but if you think about the situation, the model thing that I just introduced, there's some row dependency, the time series dependency. Imagine every time we grab the row T, we generate X tilde T, which knockoff data, the feature vector, right? And we do things separately, which means you might be generating row number 1. I'm generating row number 2. Your friend might be generating row number 3. And we're doing things independently. There's no way to guarantee that all three of us will live in a perfectly coordinated world. What do you mean that? There's no way to guarantee that our new knockoff features can maintain the same row dependency as original data matrix. So that's basically fundamental difficulty. Of course, you might argue that my argument actually was not too rigorous because there's one valid construction, because the only legitimate construction would be X tilde equal X, which means that we can start identical twins, which means we virtually copy everything. But you can argue that if you do that, we become powerless because we want to select features. If you do that, it has 0 power. So I hope that example gives you some intuition behind this problem, why the problem could be challenging. Because even think about Gaussian data, which usually is starting point for designing new learning methods, right? But even this simple situation, it's unclear how to go about this problem, right? And of course, if you're working with more complicated time series models, for example, Arch and Garch, it virtually becomes so complicated and overwhelming about how to construct the knockoff features, right? And here, basically, I want to illustrate the performance of the algorithm I'll be presenting in a second. So here, basically, we have 2 implementations of same method, TSKI. Again, I'll be introducing this method in a second. LCD and BE, there's 2 ways to define knockoff statistics for knockoff inference framework. Again, I'll go into details in a second. But here, if you look at FDR column, and for this numerical example, our target false discovery rate level is 20%, which means on average, whatever discovery we end up with, we want to make sure that the fraction of wrong discoveries should be bounded by 20%. In this case, we see that both numbers are below 20%, and plus we have quite a good power. All right. So the question is, this is just like phenomenally by chance, because this is a simulation example, right? Do we have any theoretical foundation for this algorithm? In particular, basically for this project, my collaborators and I have the following simple questions in mind. Again, this is our first attempt, and what I'm going to present represents just some very, very initial and simple ideas, and presumably there could be a lot more future developments. So first question is, how do we go beyond IID data setting, and how to design flexible knockoff inference procedure to deal with time series data and presumably with high feature dimensionality. And of course, we want to justify the algorithm has solid theoretical foundation. For example, there's two sides, right? One is the type 1 error, in this case, FDR control. On the other hand, what about power? And we know that if you want to control the type 1 error, if we do not do any rejections, which means we sit here and do nothing, of course, we make no mistake, right? Of course, we become powerless. So it's always basically a balance of the two. And another question we had in mind is, there's lots of popular ways to construct knockoff statistics. Again, that is concept I'm going to review in a second. The question is, how can we do better in terms of power? Because if you are trying to do discovery, on one hand, we want to control the FDR and type 1 error. On the other hand, we want to be as powerful as possible. Next, I want to briefly introduce the idea of our TSKI algorithm, time series knockoff inference method. So here's basically the problem setup. We have basically time t running from 1 to n, and we have yt is a scalar response variable. For example, if you want to predict inflation, CPI, this could be the target variable. And we have variable z, t minus 1, basically meaning that we cannot use the information at time t if you work with time series data. So this we have p-dimensional feature vector z. It has two components. One is for time series data, oftentimes we include basically lambda variables. For example, we have inflation today. We also have inflation from, I think we have, in this case, probably we have quarter data, right? So we have inflation this quarter, and also we have inflation index from the previous quarter. So which means we can add in the lag variables, the first lag and K1's lag. This is basically the first component of the features. And also we have WT. These are exogenous variables. For example, it could be GDP or other macroeconomic variables. And as I alluded to earlier, so in this project, we're trying to work on the problem of stable interpretable forecasting. Interpretable means out of features, all the features, we want to select subset because we want to make the model interpretable. At the same time, we want to maintain the stability, which means we're trying to control the fraction of spurious discoveries. If you think about AI application, I mentioned at the beginning of my talk, hopefully that can ring a bell. Stability could be very important in real applications, right? So which means we're trying to control the error rate. Okay, a little bit more notation. So now we have basically P features, the two parts. One is the lag variables, the other part is exogenous covariates. So which means we have variable Y and variable P. We have defined a null feature. The feature J is a null feature. Again, everything is indexed by time, right? So it's null feature if the feature is independent of response, meaning that it has nothing to do with response if we condition on all the remaining features. So basically means Xj is redundant and it can be removed. It doesn't hurt when we do the modeling if you look at distribution. And also to make things a little bit simplified, for now, let's assume that the distribution of this basically vector is stationary, which means the distribution stays the same across time t. And we have H0 basically means set of null features. And of course, you can run any algorithm like, for example, it could be random forest, could be any structural models in economics, or could be any machine learning algorithm, or it could be a deep learning algorithm. So any algorithm will end up with basically a set S hat, which means that the set of estimate features. And in this project, we're trying to control error rate in terms of forced discovery rate, FDR. So the null hypothesis states that the variable j actually is totally irrelevant, meaning that's redundant. So it's a null feature. Conditional everything else, actually, this feature is independent of response. And mathematically, FDR is expectation of this fraction, so-called false discovery proportion. It's a ratio of all discoveries that belongs to the null sets, which means null discoveries, to the total number of discoveries, basically the fraction of discoveries that are null. And we know that the huge literature and influential literature on the Benjamin Hodgeberg procedure for doing FDR control, as long as we have justified p-values. And there's lots of theoretical studies to show that the BH procedure and its variance can be theoretically justified. So the idea of basically the BH procedure is to sort p-value in ascending order, and then we choose cutoff for making rejections, meaning that smaller p-value means we have strong evidence against the null. But of course, we're running, say, p-hypothesis, so we have to adjust for the multiple comparison correction. That's why you do FDR correction. All right. But as we discussed a while back, if we're dealing with high-dimensional nonlinear learning methods, generally speaking, is highly challenging or even unclear how to get a valid p-value. If you think about the example of random forest, because it's just so popular. In this case, we can work with the knockoffs idea originated by Barbara and Candace, and also later extend to the general nonlinear model setting in the 2018 work through. So basically, the original work uses geometrical construction, and this work used basically the probabilistic constructions. All right. So in this case, we don't need the constructor p-values. Of course, we have to construct valid knockoffs data, and then we can try to do inference to show that FDR is controlled, at least in a certain sense. Okay, so next I want to talk about a basic version of the TSKI algorithm. Basically means it's a simple idea to illustrate how we can control the FDR in asymptotic sense. Of course, nothing's perfect if you use a very simple idea, right? So later on we can see how we can make things better and better along the way. All right. So if you think about the problem knockoff inference for time series data, well, if you recall the motivated example I was discussing, the fundamental difficulty came from the zero dependency, because when you, me, and your friend, we're all creating row-wise construction of knockoff feature vector. There's no way to coordinate because we don't know the population row dependent structure, right? Which means that there's no way to construct exact model X knockoffs. At least is for now is a big question mark. Okay, so then a natural idea is if somehow we can deal with the dependency, which means of course we cannot perfectly make basically the dependency go away, right? But we can try to weaken the dependency. Then probably we can do approximate construction of knockoffs variables, and that is the idea of use subsampling. Okay, so X basically our original design matrix, and it has n rows and p features, p columns. So here basically every 1 plus h rows we do subsampling, meaning that we do 1 plus h hops. We take out a first row and we do 1 plus h hops and move on to the next block. We pick one row and we do this. So make sure there's enough gaps between two consecutively picked rows. And if you're familiar with time series literature, so as long as there is basically the sampling points are separated with given distance in a time domain, under some assumptions, we can weaken and also control the dependent structure. Maybe we can basically move from strong dependency to weak dependency. All right. Of course, after we do subsampling of design matrix, we do basically the rows. We can also do subsampling to the response vector, and H basically means the subsampling frequency. The number of rows retained from this process, roughly speaking, is n over 1 plus h, or if you do some quick math, it's roughly order n over h, because later on, h is important tuning parameter. Okay, so step one was to do a subsampling, so which means every 1 plus h rows, we take out one row from original data matrix, and then we have a new design in submatrix. Then whenever I have original feature vector zt minus 1, and we can condition this feature, and then we can call the original model X knockoffs algorithm. We can construct z tilde, which means knockoff copy. Again, intuitively, z tilde is more like non-identical twin of zt minus 1, right? So probabilistically, whenever you swap original variables with their knockoff counterparts, the joint distribution stays the same. All right. So again, if you want to recall some intuition, just think about the Gaussian example I mentioned earlier. So if you do that, we can do this row by row, right? So this first row from this original data matrix, and of course we have to do 1 plus h hops. We move on to next row and we do new construction. So if you put them together, we can have design matrix X tilde, new design matrix. So after that, we have not only the X matrix. Again, X now represents the sub-design matrix. It roughly has n over 1 plus h rows. X tilde is the row-wise construction of knockoff data matrix. And Y is a sub-vector of the original response vector. And once we have the augmented data matrix, you can run any of your favorite learning algorithm. For example, you can start with Lazar, right? So sparse regression with LM penalty. So which means that for variable j, you can construct the Lazar coefficient beta hat j. And for knockoff feature x tilde j, again, because we put everything together, right? So we have another regression coefficient for x tilde j. Let's call it beta tilde j. So if you take the difference of the absolute values of the two coefficients, say wj is equal to absolute value of beta hat j minus absolute value of beta tilde j. Now let's give us basically a valid construction of knockoff statistics called LCD, Lazar coefficient difference, which has been popularly used in literature. And in this talk, I'll be introducing another knockoff feature, something called BE statistic, which I'm going to explain in full details in a second. So the intuition of this algorithm is for significant features, which means truly important features, they're not spurious. So this kind of features, we expect the knockoff statistics Wj should be large in magnitude, number one. Number two, they should be positive, all right. But for null features, intuitively, they should be smaller in magnitude, all right. So which means lower order in magnitude plus could be like roughly half positive and half negative by chance, all right. So the final step is we rank the features according to the magnitude of knockoff statistics W hat j, Wj absolute value, and then we're trying to find hypothesis to reject, meaning that the discoveries, all right. In order for basically the knockoff statistic work, for this framework, we need one more property, so we assign a flip property, meaning that with augmented data matrix, we can calculate knockoff statistics, for example, could be Lazar coefficient difference, right? So whenever you swap the variables j with the knockoffs version, so then corresponding knockoff statistics wj will have the same magnitude. The only thing that changes actually is the sign. Basically, the sign flips. And if you read basically the proofs for the finite sample FDR control for the knockoffs idea, so once we have the two properties for knockoff construction, meaning that we have the distribution exchangeability, number one. We have the conditional independence of, which means that the basic knockoff feature should be independent of true response conditional observer feature. Number three, actually, we have the sign flip property. Mathematics can show that conditional on the magnitude of knockoff statistics Wj, the signs of the null features, which means if you look at the null features, those signs basically they're IIT coin flips. It's 50% chance to be positive and a 50% chance to be negative, right? Because if you recall the construction of knockoff data and knockoff variables, they're fixed variables. They're by definition null variables because once conditioned on the observed feature vector x, x tilde x have nothing to do with response, right? And here, let me just say a few quick words about what FDR can be controlled with some intuition, all right? Recall that FDR actually is the expectation of FDP, forced discovery proportion. Actually, it's fraction of discovery that are null. So if you look at the null discoveries, all right, so discovery that are null, and because the coin flip property, you can flip the sign here, and because we don't know what features are null, we can come up with a conservative Albert Brown, which means we can use this ratio, all right? So which means if you look at running algorithm, essentially we're looking at a ratio of two quantities. The bottom is because we reject whenever we have sufficient evidence, right? Sufficient evidence here means that the magnitude actually statistic is positive and large in magnitude, sufficient large. And the numerator actually is a negative control. So the features that have large magnitude in the W statistic, at the same time, they have negative signs, all right? So here basically a simple example to illustrate. In this case, we have 10 features. We're trying to control FDR and 20%, and blue color means the positive values, and red color means negative values. And first, basically, we rank all these features according to the magnitude of the statistic from high to low, and then we work with trying to lower the threshold, because when the threshold is too large, we make zero discovery, right? Which means 0 divided 0 by definition is 0. And once we lower the threshold, we can reject, for example, in this case, we have 0 over 3 because all 3 are blue, meaning that it's positive, right? But in this case, we have 1 over 4. So which means if you're trying to lower, vary the threshold from high to low, we can have a curve of the empirical forced discovery proportion. And we're trying to find a threshold that give us basically last time this curve stays below our target level Q. In this case, 20%. In this case, we put the threshold here, and we have number 1, number 4, number 5, number 6, number 7. These are the discoveries, and we see that it's one red guy, meaning that it's one negative control. Okay, so in the end, the algorithm returns the set 1, 4, 5, 6, 7, and we know that with certain conditions, actually the FDR can be controlled at 20% level. Okay, so getting back to the basic version of the TSKI algorithm. So we look at a ratio, but if you want to be more rigorous, we have to do 1 plus, the plus version of the knockoff threshold. And if this ratio is controlled by target level Q star, again, we're trying to find a minimum T, which means last time when the curve stays below Q star. And with rejection, whenever statistically large and positive and above the threshold. Okay, and we can show that if you run the same algorithm, the FDR can be controlled, not precisely at this level, but asymptotic sense, because we have extra challenge of time series dependency. But if you think about this idea, on one hand, it's very simple, right? And we can show that the FDR can be controlled asymptotically. On the other hand, you might feel that it's probably too simple, meaning that we might be losing something. Indeed, whenever you do subsampling, we might have data inefficiency, right? So presumably, we might run into a power loss. Okay, the question is, how do we improve the selection power of this basic time series knockoff inference procedure? All right. Okay, so here I want to briefly mention some ideas. The first idea is basically knockoffs with copies, which was used in recent literature. All right. So the algorithm actually is very simple. You have the original design matrix X, right, and the response vector Y, and you divide data into two halves. Okay, first half and second half. So for now, let's apply the basic TSKI algorithm to the first half data, meaning that we do subsampling here, which means we have sampling frequency H, and this is X. We construct knockoffs variables, and we have response, again using subsampling. But now we have second half, right? We do something very simple, which means we virtually copy data from second half. The second half, the original design matrix, second half, the original design matrix, even for knockoffs, which means if you look at the second half, they are identical twins. But the first half, as I mentioned earlier, they cannot be identical twins. Otherwise, we'll run into a power issue, right? Of course, for response, we attach the second half. At the same time, you can swap the procedure, right? Which means you can return the first half, which means we have perfect copy for first half, and we can apply apply the subsampling to second half data, which means we run a basic variant to second half. You might argue that, well, both variants could be okay, right? On the other hand, whenever you do the splitting, we might lose the data efficiency, right? Which means, presumably, we want to combine information from two constructions, right? If you swap the two, okay. Indeed, we can do that. And here is basically a simple idea. The double knockoffs inference algorithm. Okay, so as I mentioned, basically, we divide data into two halves, and then we first, for example, we apply subsampling to the first half and copy the second half, and then we solve the two. So every time we apply this knockoffs inference procedure, but because we combine information from two constructions, so now we have to divide our quota by 2. So every time our quota now is Q star over 2, 1/2 of the target level. And we have discovery. In the end, combining means we do union of the two sets. And mathematics can show that under certain conditions, the FDR can be controlled asymptotically at this level Q star. And here, the double, which means dividing the two halves, right? So of course, just illustration. You can easily come up with the multiple knockoffs idea inference, because if you think about knockoffs idea, it actually is sampling idea, because we're trying to generate fake data in a nice way, and according to some nice distribution, right? Distributional exchangeable symmetry. Of course, you can generate your own data. I can generate my own version of knockoff data, which means our algorithm, even if we run the same algorithm, we end up with different sets, right? So the question is, how do you leverage the sampling procedure and try to get more out of this inference, which means we can combine different sets of knockoff data matrices. Another question is, as I mentioned, there's many ways to construct knockoff statistics, but the Nassau coefficient difference LCD has been popularly used in the literature because Nassau is a very popular learning method. LCD actually is a very simple construction. But the question is, can we come up with more powerful knockoff statistics? All right. So next, I want to provide some insight into the question with, of course, we will start with some simplified model setting. So in this work, we suggest a new model, knockoff statistics, so-called BE, backward elimination ranking. So for now, we constrain ourselves to the linear model setting. The major reason is, if you work, one reason is because we want to do power analysis. If you work with linear model, the signal strengths, actually, those conditions can be easily identified. If you go to beyond a linear model, things could become much more complicated. That's why we illustrate the idea of BE with this linear model setting. All right, so In short, we have a response vector V, and we have augmented data matrix V. So now we have two P columns because we have P original columns, and also we have P knockout features. And we can try to find a sparse approximation based on the 2P features, which means trying to approximate our target V with hopefully a sparse model. And if you run the same algorithm, there's many ways you can solve the problem, at least approximately. And you can end up with a sparse set M hat 1. For example, algorithm might give you, say, 20 variables. And then let's run the following algorithm. Let's pass the set to M hat 2. The following actually is an iterative procedure. So whenever M hat 2 is now empty, we do the following. Every time we do leave one out, which means we get rid of feature J and we do a refitting. Again, we're trying to do sparse fitting. We're trying to find feature J that minimizes this loss. All right. Intuitively, know that if J is important, if you remove important variable from the model, we know that the loss will jump up, right? And if you're trying to minimize this guy, meaning that the variable we remove from the current iteration should be the least useful one. If you think about basically a linear model setting, intuitively, it's like if you run basically the feature-wise t-test and trying to remove feature that has the smallest t-statistic or largest the p-value from t-test, all right. And then we define the BE knockoff statistic WJ in the following way. If the variable actually belongs to original set from index between 1 through p, it should be a positive number. And actual value records the exact order the variable gets removed. Maybe the first one to remove, second one to remove, or third one to remove. All right, but this one is positive. On the other hand, if feature belongs to the knockoff set, which means that the index between p plus 1 up to 2p, so we should flip the sign. It should be negative value. Again, the magnitude is same as the previous one. Exactly the rank of the feature, meaning that the exact order in which the variable gets removed from the model M hat 2. All right. So we run this iteration until we end up with empty set. Of course, for all the variables that are not in the set, we assign 0 to feature ranks. We mean that for the corresponding feature, the B knockoff statistic will be 0. We know that 0 meaning that we don't have any evidence for assessing the significance of the variable. All right. So intuition is if variable is important, the variable should stay until a later stage of the iteration, meaning that around the later stage, this variable might get removed. All right. Okay. So I mean that for important variables, if you look at the definition, intuitively it should be positive, and also should have large magnitude because it gets removed at a later stage. On the other hand, a variable is not a variable. Keep in mind, knockoff feature by definition is also null feature, right? Fake variable, meaning that it will have so basically it means that it will have smaller magnitude because null variables tend to be removed early on. Second one is because both original feature is a null variable, and we know the knockoff feature is also null feature, right? So it's hard to tell which one will win the competition, meaning that maybe 50% will be positive, 50% will be negative. So this gives us some intuition for the FGR control. And we can incorporate all the ideas I just mentioned, for example, double knockoff inference and being knockoff statistic into a general version of TSKI algorithm, which means that on one hand, we can do FGR control. On the other hand, we can make sure that the power is decent. All right. Oh, Yoshi, how long is the talk? So when should I stop? Because I just realized that's already 1 hour. Yeah.
Yeah, actually 1 hour, but maybe so you can have several minutes.
Oh, okay. All right. So, okay. In that case, I'm trying to wrap up in the next few minutes. All right. Okay. So one natural question is there any theory behind the procedure, right? I mean that can we show that FDR can be controlled and power could be decent? All right. So there's one key assumption behind this work, because as I mentioned, the major difficulty comes from the time series dependency across the observations, right? So in this case, we assume the actual state beta mixing condition with exponential decay. We assume we have a stationary Markov chain with transition kernel, and once you do subsampling with frequency h, hopefully the dependency can be much weakened, and we can show that mathematically. Indeed, basically we can bound basically the distance to idealize the model with independent rules under the total variation distance. All right. And we can show that this condition can hold for many popular time series models. All right, so long story short, so for the basic procedure, we can show that if you run the same algorithm, the FDR can be upper bounded by Q star, which is the target, plus additional term, a constant times rho, which is a geometrical factor coming from this previous property, to the power h, the sampling frequency times n. So we know that as long as h is not too small, this can be vanishing asymptotically, meaning that asymptotically we can control the FDR. And also we see that this additional term characterizes the precise price we need to pay. We move from IID data to serial data with we have data dependency. All right. And also we have the theory for double knockoff inference procedure, meaning that if you do the sample splitting and then swap, combine information, FDR can be controlled. But we have factor 2 because we do 2 constructions. And also we formally justify the power of BE statistic on a linear model setting, meaning that we can show that asymptotically the estimate set actually can contain the true model, which we know that is your screening property, of course, meaning that asymptotic power is 1. Okay. And also we have numerical studies to illustrate the performance of this, this method. So here basically I just mentioned one simple example. The error model with exogenous variables, meaning that this is error model and this additional covariates. And here's basically a table summarizing information. So as you can see that if you look at the FDR column, the target is actually 20%. Indeed, we see that all the numbers are below 20%. And plus, this is plus version, which means theoretically can be controlled at 20%. And also if we move from lower sample size to higher sample size, the power improves, which makes sense, is sensible, right? Because we have stronger signal strengths. And if you compare BE statistic with LCD, we see that we have power gain. And if you look at an error component, the power gain actually is more pronounced. And we have additional examples from the paper. And also we apply this idea to a real data application, meaning that we're trying to forecast the inflation based on the popular FRED MD data set. Actually, indeed, the feature dimensionality is comparable to the sample size. And the short version is the TSKR method actually with BE statistic performs the best across all the methods. It has lowest prediction error, plus the estimate set actually is highly stable because we have FDR control. You might have noticed that the LCD version, even though theoretically has FDR control, but we have basically one thing I forgot to mention that because the use of copies, the knockoff feature and original feature, they tend to be highly correlated in asymptotic sense. That's why if you run LCD, the your way of knockoff static construction, we might have power loss. That's why basically the prediction error tends to be higher. Otherwise, FDR side, they should have similar story. Okay, so to summarize, in this work, we looked at the problem of feature selection on FDR control for time series data. And we suggest basically a simple method time series knockoff inference. And in addition, we introduced a new knockoff statistical construction method based on feature ranking, the backward elimination ranking method. And we show some theory justifying the asymptotic FDR control. And also we show that under some model setting and assumptions, the power can be appealing. And of course, as I mentioned, our attempt, basically just first attempt for this problem, and due to the time series nature of data, is highly challenging, highly complicated. There's lots of interesting and challenging open questions. And with that, I want to stop here and just thank you all for your attention.
Thank you very much, Jinchi, for the very interesting talk. So, any question, comments from the audience?
Professor Liu, thank you very much for the very insightful talk. I have some clarification questions.
Sure, thank you, Jinchi.
Yes, so for the double knockoff procedure, right, what is the intuition that when you have the second half, which is exactly the same copy, then you have the power improvement? Can you give us some more intuition about this?
Yeah, good question. So if you think about, for example, the basic version, right, which means you only do subsampling. For example, in that case, the effective sample size will be n over h, for example, because if we look at, by the way, I did not get a chance to cover the theory. So there's some assumptions on h, meaning that if you want to have asymptotic FDR control, h cannot be too small. But on the other hand, sample size will be compressed, right? Meaning that our signal strength will be much weaker. But basically for the knockoffs with copy and also double knockoffs inference procedure, if you do sample splitting, apply sample sampling to one half and copy second half. So intuitively, because you retain half of the sample, and you can try to strengthen the association between the response and our features. Because if you look at the basic second half, they're authentic data, right?
Right.
Just basically mean that you're trying to increase the effective sample size from n over h. For example, h could be growing. This will be a shrinking number, right, relative to n. If you do basically with a splitting idea, you essentially you improve sample size from n over h up to n over 2h plus half n. So which means before the actually smaller order of n, but suddenly now it becomes basically same order n. But I did not mention, because everything comes two sides, right? On one side, well, we boost the signal strength because we have more sample size, more information. On the other hand, this will significantly increase the correlation, collinearity between the knockoff features and original features because we do copy, right? Just imagine.
Right, you were talking about the non-identical twins, right? So if your second half is exactly the same, as you mentioned, this might also affect power. Yes,
right. But interesting in this case, this is more like dilemma for time series data because on one hand, we want to retain as many observations as possible, right? Because that gives us better power. Right. But if you look at, but on the other hand, if you retain more, we have more constraint for the dependency structure, which means it's more difficult to control FDR. It's more like a double-sided, so we need to find a sweet spot. But interesting for this case, if you go to the technical details, even though by construction, asymptotically the knockoff feature with the copy idea and original features, they will be highly correlated asymptotically. But we can still tease out a signal. And if, for example, if you work with the feature ranking idea, B statistic. On the other hand, if you throw in some more traditional learning methods, we might run into issue precisely because the collinearity. Yeah, it's quite interesting. Yeah,
I see. So it seems, in some sense, the power issue is from the subsampling, right? So
right.
So I was just wondering why other resampling method don't work in this case. For example, can you use bootstrap in this case instead of using subsampling?
Good question, Wenjie. So yes, actually I was chatting with Yoshi prior to the to the talk, right? So we'll also think about this question along line for a while. The fundamental difficulty, it's actually it's a dependency. So if you think about subsampling, yes, there's many ideas. But for this one, actually, we work with basically subsampling with some constraint on the frequency. So, but presumably you can do other constructions. But at least it's unclear to us how to rigorously control FDR, which means if you're thinking about algorithm, there are many ways to implement. But on the other hand, so whatever you do, in the end, we have to deal with the dependency issue, meaning that you want, basically our target here is trying to control the false discovery rate. So, and if you look at the current literature, almost all the basically existing works have assumed normally it's like ID data, right? Or independent rows, and you can do reduction. But this case, yeah, so it's quite interesting. So the dependency in this case can hurt you.
Very complicated. I see.
Yeah, right. So as I said, basically, there's lots of interesting questions in this domain, because what I present just basically is a very simple and initial attempt, right? Yeah.
I see. Thank you so much. Thank you.
Yeah. Thank you, Jinchi.
Any other questions, comments? So I have a question. So
sure,
what's the assumption on the cross-sectional correlation?
For that one, actually, the cross-sectional actually is general. For example, yeah, right. So if you think about Gaussian data, right, which means the column dependency could be general. But in this case, the fundamental difficulty comes from the row dependency, basically the time series dependency, right? Yeah, yes, right.
And also, so your procedure, BE procedure, assume, does this assume the Markov chain only, or maybe is it possible to extend to the other time series structures?
A very good question, Yoshi, because for a while, we did not know how to move forward, right? And then we came up with a simple idea, and of course, we need some justification, right? So basically, a stationary Markov chain with, the beta mixing property, that basically is a mathematical assumption we imposed in order to prove the FDR control in an asymptotic sense. And in this work, basically, we did verify the condition for some popular time series models. But again, as you know, basically, you're expert on the time series side, right? So there's so many popular time series models, and actually, it's open play field. And so, which means from the methodological point of view, there could be space for developing new methods, and also mathematically, it's largely it's a big question mark how to even justify the FDR can be controlled. Yeah.
So, and also, yeah, maybe I missed your talk, but if we estimate the model and construct the knockoffs, it's not the exact knockoff, right? So
okay.
Due to the estimation error. How to avoid this issue?
Oh, Yoshi, you asked a fundamental question here. So actually, I think I did not get a chance to clarify on that. So essentially, for this work, basically our focus was purely on the time series domain, which means we want to extend the original ModX knockoff idea to time series data. So we stick with the assumption from the original ModX knockoff paper. We mean that we assume that the covariance distribution is known, but now we have to deal with the time dependency. So of course, yeah, if you want to implement, there's many methods we can use, right? For example, we can use, for example, the iPad approach, right? Or we can use, for example, actually in the numerical study, I did not get to mention, in the paper, we use the second order approximation, meaning that we estimate the covariance and try to match the first two moments and to generate knockoffs. But that is empirical. Getting back to the question, that will be a good future research problem, because the current problem is already quite lengthy. So that's why we stick with this simplification to this side. But in the next natural step is how to incorporate estimated covariance distribution, right? Yeah.
Okay, thank you very much.
Thank you, Yoshi.
Any other question, comments? So maybe, so Wenji, how do we do?
Yes, I think it's almost already the time and
Okay.
yes. Thank you very much, Professor Liu, for giving us such a frontier talk about the FDR control. Yes.
Thank you, Wenji, Yoshi, and thank you for everyone for attending. Yeah.
Thank you so much.
Thank you. Yeah.
Thank you.
Yeah.
Thank you so much.
So Yoshi, do you want to stay here and for chat, or you want to?
Yeah, sure.
Okay.